Hey guys, welcome back to Bison Maths. This is the second in a series of videos that I'm doing to help you memorise everything that you need for your Maths A-Level for edXL. The first one was on Pure. It's on my channel page. If you haven't checked it out yet, go and have a look for it. This one's going to be on mechanics, and I'll be doing one soon on statistics. If you haven't checked out my channel before, you should go and see that I've got hundreds of videos of my real life lessons with students at my school, and it's a different kind of way of learning. It's like being in a classroom rather than just watching a video. All the videos are organised into playlists, and they all match up with the official Pearson edXL textbooks, and I've got nearly all of the chapters done by now. There's also stuff there for further maths, so if you're taking further maths, go and check them out. And of course, if you like this video, please do hit the thumbs up and do subscribe to my channel to get more of these as they get released. So for this mechanics video, people usually think that there are lots and lots of different topics in mechanics, but what I'm going to really try and convince you of is that there are actually just two big topics. There are kinematics, which is about how things move, and there are also forces, which are all of the things like connected particles, lifts, and moments. If we can break it down into those two types of topics and then discover what skills we need, I think mechanics is going to be a really strong area for you. So I hope you agree with the way that I've broken things down here. Let's get on with the video. Okay, so you can see here that I've organised my memory page for mechanics into these two sections really. There's one for kinematics, which is about how things are moving, and then there's one for forces. So we're going to get started by having a look at the kinematics section that we have up here. Now, when you have a question in mechanics, one of the first things that you should really do is decide, is it talking about something with constant speed? Does it have constant acceleration, or does it have variable acceleration? Because that's going to determine what kinds of skills that you need. So we'll get started by having a look at something that has got constant speed. In other words, the acceleration is equal to 0. So we know from GCSE the distance is equal to speed multiplied by time, speed times time. And sometimes you need to convert between kilometers per hour and meters per second. So to convert from the kilometers to meters, you multiply by 1,000. And then to go from the per hour to the per second, well, you would divide it by 60 to find out what it is per minute, and then by 60 again per second. So you multiply by 1,000, divide by 60, divide by 60. And to go from meters per second to kilometers per hour, we just do the opposite. So we're going to divide by 1,000, and we're going to multiply by 60, and then we're going to multiply by 60. Now, if you had constant acceleration, you could actually use the SUVAT formulae. Now, I've put these little Fs with a heart next to it to say that it's in the formula book, but you should memorize this off by heart. So these kinematic equations for the constant acceleration, you should know these off by heart. That is that V equals U plus AT, S equals UT plus a half AT squared, S equals VT minus a half AT squared, V squared equals U squared plus 2AS, and S equals a half U plus V brackets T. The thing to note about these equations is that each one of them has one of the S, U, V, A, or T missing. You only ever need 3 variables, and you then have a fourth one that you're trying to find. So for variable acceleration, you'll know in the question of its variable acceleration as it will be expressed in terms of t. So in order to do variable acceleration, I write them in this order. I start off with the S because that comes first in SUVAT, then V, then A. S, U, V, A, T. So they go in that order. And if you wanted to go from S or X, because sometimes they might say that the displacement is in terms of X, or is expressed as X equals, to go from the displacement to the velocity, all you do is you differentiate it with respect to time. And to go from the velocity to the acceleration, you differentiate it with respect to time. So if you are going down, you differentiate. And that's how you remember that going down is differentiating. You can also think of the units as well, but this is my quick way of remembering it. And then if you're going to go upwards, you do the opposite. You're going to integrate with respect to time, obviously making sure that you add in your constants of integration as well. So that's how you're going to tackle those first 3 kinds. Then we're going to have a look at the different graphs that we have here. So we've got some speed time graphs. Now this first one, it's pretty obvious that the speed is going to just remain constant because we've said there's no acceleration. The second one, we've got some different stages, and the third one we can tell that it's variable that we have here. So in general for these, the distance travelled is going to be the area under the line. And you can see in this first one here that if this is the speed that we have here, and this is the time, well, the area underneath it is the distance. It's a rectangle, and we can see that that distance is going to be the speed multiplied by the time. Now for this one here, you should split this into a few different shapes. You could do a triangle, a rectangle, and a trapezium, but I just see this as two trapeziums, and you need to know that the area of a trapezium is a half brackets a plus b h. If you were going to do SUVAT for this graph, you can only do SUVAT in 3 different stages because there is not constant acceleration throughout the whole thing. There's constant acceleration for part 1, part 2, and part 3. So you cannot apply these SUVAT equations for the entire journey. It would have to be piece by piece. And then for the last one, for the area under the line, well, we've got to be careful of this section down here because it goes into a negative area, and negative areas will not give us the correct distance. So if we were going to integrate this one, we would integrate the velocity with respect to time between 0 and 4 for that first section, and then we would add on the magnitude of the integral of the velocity between 4 and 6, between those limits. This is what the distance travelled would be. So you need to make sure a negative area that you take the magnitude of it, which I've represented here with these modulus lines. And then the last thing that we need to know is that the acceleration is the gradient of the line. And so you can tell really in this first one that the acceleration is 0. Here you can see there's there's 3 different accelerations. And in this last one, we can see that the acceleration is variable. Okay, then what we've got down here is some vector motion stuff. This is usually done as a separate topic, but I think it makes sense here. So if there is no acceleration, you just use a variation that the position vector is equal to the initial position vector plus the speed multiplied by time. Time is not a vector, so it doesn't get underlined. And then the SUVAT equations get adapted so that you have v equals u plus at, r equals the initial position plus ut plus a half at squared, and you get the initial position plus vt minus a half at squared. The other ones don't work so well because of the squaring in v squared equals u squared plus 2as. And then this last one that we've got here, it's the same as above. You're going to write them in that same order. To go downwards, you differentiate, and you just differentiate the I and j parts separately, and to go upwards, you integrate. Both of them with respect to time. Now for projectiles, I've actually drawn these 2 arrows here because projectiles are a combination of this set where there is no acceleration and this set where there is constant acceleration. And that is here when we have the horizontal motion, the acceleration is 0. So we just use things like we've got above, like distance equals speed times time. And for vertical motion, the acceleration is minus g. And those 2 things will separate that motion into horizontal and vertical. And the thing that connects them together is t. These are connected by t, time, I mean. So if they wanted you to find the speed and direction of motion at this point that I've got here, A, what you would do is you would find the horizontal speed using distance equals speed times time. You would find the vertical speed using SUVAT. And then if you wanted to find the speed, you would do Pythagoras. And if you wanted to find the direction, you would use the inverse tan. And that's to do with this diagram we've got here. If we're trying to find the speed and direction, we find the horizontal speed and the vertical speed. You'd use inverse tan to find that angle, and you'd use Pythagoras to find the length of that hypotenuse. Now for the vector motion, I just wanted to add in a couple of things that are usually short parts of questions. If it said that it is moving in the direction 2, 3, moving is to do with its velocity, and it's not going in the exact velocity of 2, 3, but it is going parallel to it. So you put that k in front of it to show that it's parallel. If it says it is northeast of the origin, that means that its position is northeast would be 1, 1 of the origin, and it would be some multiple of that. But really what we can see here is just that the I component would just be equal to the j component. And that's because it's northeast like this. The other place where the I and j components would be equal to each other is down here. So we get that I is equal to j here and I is equal to j here. So that's for southwest and northeast. If it was southeast or northwest of the origin, we would get that the I component was equal to the negative j component for both of these, or the j component was equal to the negative I component. So I'm just going to add that in that we've got here. This is where they are equal to each other and both plus, and this is where they are equal to each other but one of them is negative. Okay, we're going to now have a look at some other bits to do with forces. We're going to be looking at some modelling assumptions that we've got here. So for these modelling assumptions, for a smooth pulley, people often say, okay, that means that there is no friction. But how that has affected the model, or how we've used that in our calculations, it means that the tension on either side of the pulley is equal. And for a light string, people say that has no mass, if the string has no mass, but how we actually use that in the model is it means that the tension is equal throughout the string. If you imagine a really, really heavy rope, the top of the rope would be having to support the whole bottom part of the rope, so the tension would be much bigger. The bottom of the rope wouldn't even be having to support the top part, so the tension at the bottom would be smaller. That's because it has mass. So if we have light string, we can just say that the tension is equal throughout. If it's an inextensible string, if we've got connected particles, this means that both particles have the same acceleration. If it was extensible, it'd be stretchy. You could have one of them moving and the string just stretching, the other one not even moving. When something is a particle, that means that we can ignore air resistance. That's a really common one. So I'm going to say another one too. We can ignore air resistance and we can ignore rotational effects. And that's because it has no dimensions. A rod means that something is rigid, so it doesn't bend. It also means that it has no thickness. So when we model things as rods, we're saying it has no thickness. So if they ask you to say what's the limitation of the model, it's not very realistic that a plank or a beam is going to have no thickness. And I've got some more obvious ones here, like if something is smooth or rough, but they're pretty obvious. Smooth, no friction. Rough, there's friction and stuff like that. Okay, so that's everything to do with kinematics so far. Really what you need to do at the beginning of a question is you say to yourself, is it constant speed, is it constant acceleration, or is it variable acceleration? And it will then tell you what kinds of skills that you'll be using. We're now going to have a look at forces, which is probably the bigger part of this topic. So to start off with, if something is in equilibrium, these are the kinds of words that you might see. It would say that it's static or at rest. It's on the point of slipping, or there's limiting equilibrium, or that it has constant speed. What this means for all of these is that the forces are balanced. And more specifically, it means that the left and right forces are equal to each other, and the up forces are equal to the down forces. And then I've got here a vector forces triangle, and you can see when you draw these vectors from nose to tail, so that they kind of follow around in a flow diagram, they go back to the beginning from where they started. This is because if you add vector forces together, I'm just going to be doing 3, but you could be doing it with more or less. If they equal 0, that means that it is in equilibrium. Then we move on to dynamics. All that dynamics means is that you can use F equals ma, and I've said that if none of the above are true, it is either accelerating or decelerating, so there's an imbalance of forces. What you do is you resolve using F equals ma in the direction of motion. That's always the best way to do F equals ma in the direction of motion. With vectors, you use the vector version, which is F equals ma with the F and A underlined, where F is the resultant force R, and the resultant force R can be found like this by taking however many forces you've got and adding them together. I'm just doing it with 3 forces. You could have 4, you could have 2 forces, you could even have 1, and that would be your resultant force. Okay, let's talk about friction. So friction always opposes the direction of motion or the direction it is about to move in. Because it may not be moving, but it may want to move in a particular direction. So if it's static, friction is going to be less than or equal to mu r, where r is the normal reaction. If it's in limiting equilibrium, meaning it's about to move, or it's dynamic, so it's accelerating, then friction has reached its maximum and friction is equal to mu r. Now I've written here that mu is greater than or equal to 0. That is true. Sometimes you see that mu has to be less than 1, but this is not true. You may find some calculations where mu could be 1.6 or 2, but generally mu is going to be less than 4 or 5, but there's no upper limit really. So on slopes, they love these kinds of questions where they say, is it going to move? So I'm just going to quickly add some diagrams on here. I think this one is going to want to move down the slope, which means that the friction would be going up the slope. And when you would put the weight coming down, we would resolve it into these forces. And so the one that's bringing it down the slope is mg sine theta. So if mg sine theta is bigger than the maximum value that the friction can take, then it will move. And it will move down because it's bigger than the friction can take. If mg sine theta is less than or equal to the maximum value of the friction, it will remain at rest. Okay. Now we're going to start talking about some of the force diagrams. We're going to go into some basics here. To resolve forces, we know that there are two ways you can split them. Along the bottom, you have that it's adjacent to the angle, so it's f cos theta, and then we have f sine theta because sine goes with opposites. It's all to do with the angle. Now, if you have tension, we're concentrating on what these particles feel. This first particle that I have here would feel that it is being pulled. So that's why the tension goes in this direction. This second particle feels that the tension is pulling away from it. So tension, the arrows are going inwards. For thrust, this is where they kind of feel like they're pushing in. It would feel like the pole is pushing into this one. And for this one, it's going this way. So it kind of feels the opposite direction, but this is how they should be for tension and thrust. So boxes on boxes and lifts here. Now I've got a diagram. This is meant to be representing a lift. There are two boxes inside this lift. There's box A, which has small m kilograms. Box B is capital M kilograms, and the lift itself is L kilograms, and it's being held up by a rope that we've got here. We're going to try and think about all of the different forces that are acting on these. So for A, it experiences, and we're always drawing it from the point of view of the particle, it experiences its weight, which is mg, and it experiences a normal reaction, which is from B pushing upwards. So I'm just going to write this here. This is B pushing on A. That one's pretty simple though, okay? Now, B is going to be experiencing its weight, which is mg, but it doesn't experience A's weight. It actually experiences the normal reaction over here, but going in the opposite direction because of Newton's law that says that each action has an equal and opposite reaction. So it feels R coming downwards, and it also feels from the bottom of the floor of the lift, it feels a different normal reaction, which is N. I'm just going to call it N, and this is the floor pushing on B. That's where people get really confused with this diagram. Now for the lift, I'm ignoring the particles that are inside the lift. I'm just concentrating on the lift here. If you were that lift, what would it feel like? Well, you would certainly feel the tension pulling upwards. You would feel your own mass of the lift, and that mass of the lift is going to be L kilograms, so it will be Lg as weight. And it doesn't feel the weight of A and B. In fact, it feels this normal reaction of the floor pushing on B. It feels B pushing on the floor with that exact same amount. So there's going to be an N pushing it downwards like this. That's where people get confused, because you'll notice in these three diagrams so far, there's only the weight of A, the weight of B, the weight of the lift. There are no other weights associated with it. It is all different reactions, okay? And then for this last one that we've got here, if you consider the whole system, you can consider that there is the tension, and then coming downwards for the weight, we're going to have little m plus big L, G. The whole system is probably a good one for this, but sometimes they ask for some normal reactions of the bits that are inside. And I've got a video on all of these things to do with lifts, which I'll be linking in the description, so you can check that out if you find that confusing. Okay, let's now have a look at some more things to do with force diagrams. So we're going to do connected particles, and then afterwards I'm going to talk us through what the standard method would be for this. So maybe this one is like a car towing a caravan. Now, to begin with, I'm going to say if this was the car, there may be some driving force, which is D, and it would also feel the caravan pulling it backwards, and that would be with T, that tension in the tow bar. And there may be some kind of resistance, some kind of friction on the road, which I'm going to call R1. Now, if you imagine that you were the caravan, you would feel that the car was pulling you forward with force T, and there may be some other resistance that you've got here, which I'm going to call R2 for that resistance. Obviously, there's going to be normal reactions and weight, but I'm just keeping mine on a level plane here. Okay, this next one that I've got is going to be two particles with a pulley. So let's start off with this one over here. I'm just going to give it a mass of M1, so there's going to be M1G, and there's going to be the tension pulling it upwards. And for this one, if you imagine being this particle, there's going to be its weight, which is M2G, and the tension pulling it upwards. So each time I use a different color, I'm imagining that I'm a different part of the diagram. And so my last diagram the last thing I'm going to think about is what it feels like to be the pulley. Well, the pulley feels tension pulling it down here and tension pulling it down here. And it also feels a normal reaction pushing upwards like this. So if I was just going to quickly draw that diagram again that we've got, let's just quickly switch this. I would have, for the pulley, these different forces that would be acting. So there would be a normal reaction coming upwards, and it feels the tension coming downwards in these two places. So for the pulley, the normal reaction is 2T. Each colour is me imagining on a different part of the diagram and what it would feel like to be that part of the diagram. Sounds strange, but it's the best way to think about mechanics. Okay, this time I'm just going to do one type of connected particles over a pulley. I'm going to say it's on a rough slope, so I'm going to add some forces in. First of all, for A, there is going to be its weight, which is going to be M1G. There is going to be its normal reaction. There is going to be the tension pulling it up the slope. And there is going to be the friction, which is opposing its motion. I'm presuming that it's going in this direction, but it may not have to go in this direction. It could be going down the slope. Obviously, what you would need to do is resolve this force into its two components. So you would have M1G cos theta because it's adjacent to the angle, and M1G sine theta for that one running that's parallel to the slope. Now I'm going to do in red here for this B particle. It's going to have its weight, which is M2G, and it's going to have the tension that is pulling it upwards. Now again, I'm going to use this green colour to think, what would it be like if I was the pulley? Well, the pulley feels the string pulling it in these two different directions, and as a result, there's a normal reaction like this. Now, I'm going to do this diagram in a little bit more detail because this is always a 2 or 3 marker that people miss out on. Now, if this angle at the bottom is theta, this one at the top would be 90 minus theta, because obviously this is a right angle down here. So when I just come over to this diagram that I've got, we said that this whole angle was 90 minus theta. So each of these individual angles that we've got here would be 90 minus theta over 2. And it's experiencing these tensions in these two directions. And there is a normal reaction that's going in that direction, exactly halfway between them. So if I were just to resolve these forces, I'm trying to find out these two red arrows. The red arrows are adjacent to that angle, so they would be cos of 90 minus theta over 2, which means that R is going to be 2 lots of those red arrows. So it's going to be 2t cos of 90 minus theta over 2. These ones that I've got here and here are going to cancel each other out, which is why I've basically ignored them there. And they're cosine because they are running adjacent to the angle for that. So that's how you find the normal reaction or the resultant force of these two strings. Resultant force and normal reaction are going to be the same for the pulley. So what's the method that all of these follow? Well, starting off for connected particles, you do 2 F equals ma. And F equals ma in the questions, they will sometimes refer to these as an equation of motion. After you've done both of those, what you'll do is some simultaneous equations. That will usually be to find out what the acceleration and the tension are, but it could be other variables as well. Then there's always that part where the string is going to break or a particle is going to hit the floor. And there's usually a standard method that we do for this. So you start off by doing some kind of suvat, and you do that to find out V for one of the particles, because later on it will become U after the string breaks or after the particle hits the floor, after one of them hits the floor. Then what you do is you find out a new value of the acceleration, and there's going to be a new acceleration because after the string breaks or one of them hits the floor, the tension becomes 0, and that's going to change the acceleration. And then there's going to be some more suvat after you've done that, and you will use the new acceleration, and your value of u will be the v from before. And that you have to kind of think to yourself carefully about how you're going to do that bit. So that's your standard method. F equals ma, F equals ma simultaneous equations. That's usually the part A and B. Then you can do some suvat, new acceleration, more suvat. That's usually going to be the last parts of the question. It's really a good one to be thinking about. Okay, we're nearly there. We're going to be thinking about rigid bodies and how the forces are, and then we're going to discuss this with moments as well. To start off with though, if something is uniform, this means that the weight acts at the center. If it's non-uniform, the weight doesn't have to act at the center. If it's on the point of tilting about A, well, for this diagram here, if it's about to tilt about here, that means it's just about to lift off from B. It means that there is no normal reaction at B. So the normal reaction at B is equal to 0. If it was going to tilt about B, then the normal reaction at A would be equal to 0. Okay, when you're doing force diagrams for rigid bodies, you always think about the forces that are acting on the beam. Okay, you're imagining that you are that beam. So it would feel the 2g weight pushing down. It wouldn't feel the normal reaction of 2g because that's what the 2 kilogram weight would feel. There would then be some kind of normal reaction at A and some kind of normal reaction at B. And I'm going to say this is the uniform rod, so there's going to be the weight of the rod. You'll notice I've drawn the normal reaction at A and B as different sizes to try and remind us that they're not necessarily going to be the same size as each other, and they definitely wouldn't be in this situation that we've got here. So this first diagram that I've got is a ladder scenario, and a ladder is going to have the weight that would be pushing it down. The wall would be pushing it outwards with that normal reaction. The floor would be pushing it upwards with a normal reaction as well. I'll have to use 2 different letters there. And this ladder, if it was on a slippery floor and a slippery wall, it's going to want to move in this direction, which means that there would be some friction to the right. It's going to want to slip downwards, so there would also be some friction upwards as well. This second one we've got, this is meant to be a rod that is being suspended by a string. So there would be some tension, and it's in that direction because that's what the beam would feel. There is going to be its weight, which I'm going to call W. And then over here, there's definitely going to be the wall pushing backwards. I like to use the letter X for this because it's horizontal. And then there's either going to be an upwards force on this hinge, or there's going to be a downwards force. You just make a choice. Put it either up or down. If you get a negative, you put it the wrong way around, but there's no harm in doing that at all. So I'm just going to get rid of that second one. I'm just going to keep it going upwards. And then this last one, it looks like I've got a beam or a rod resting against a peg. I'm going to say it's a smooth peg, so there's just going to be a normal reaction like this. And then there's going to be the normal reaction from the floor. I could use R, I'm going to use Y to make it seem similar to the previous one. And there's also going to be some friction. I could use friction, or I could use X. And there's going to be the weight as well. Now, if you wanted to find out the overall reaction of this bit down here, all you would do is Pythagoras to find out this overall reaction like this. And to find out the angle of that overall reaction, you could do trigonometry, you could do inverse tan and find out what that angle was. It's also going to be true for this one that you've got over here. You can do that same process. Okay, so we're nearly there. We're just going to be thinking about what moments actually are. To calculate a moment, you do the force and you multiply it by the perpendicular distance. You can, if you want to, do the perpendicular force multiplied by the distance. I don't teach it that way, but there's no harm if you do it either way, they both work. And all I've written here is that the anti-clockwise moments will be equal to the clockwise moments if it's in equilibrium. Now, there are only 3 things that you can do in these moments questions. If it's horizontal one, there's only 2 things. But the 3 things that you can do is, first of all, you can resolve it up and down. And when you resolve this up and down, you can clearly see, because it's an equilibrium, that y is equal to w. The second thing is that you can resolve it left and right. And when you resolve this left and right, you can clearly see that x is equal to p. Obviously, you can't do number 2 if it's just a horizontal thing. But I'm going to get rid of those brackets. And the last thing that you can do is you can take moments. And usually the best place to take moments is probably going to be this bit that we've got down here, when moments about A. You just pick one place to take moments. Now, for these different forces that I've got here, this one, X, is not going to have any moment because it's going straight through A, nor is Y. So I'm just going to concentrate on doing this W force. Now, this W force here, its perpendicular distance is from here to here, which is A cos theta. So that first bit, which is trying to make it go in the clockwise direction, is going to be A cos theta multiplied by W. And that is going to be equal to the other one, which is going to be up here. Let's just quickly switch a color. And for P, you can extend that line of action of the force. The distance between these, well, this is theta. The hypotenuse is 2A. So it's going to be a 2A sine theta. So the moments about A are going to be 2A sine theta multiplied by P. Then all you do is you take number 1, number 2, and number 3. You solve them in whichever way you can to get whichever answer that you're looking for. So this is everything that you need to know for mechanics for year 1 and year 2. Lots of this actually is quite simple, but lots of it looks tricky. So practice, 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 and it's going to make you do really well in this topic. Okay, so that's it. That's everything you need to know for mechanics for year 1 and year 2. If you found that useful, please do like the video. Go and check out my channel, subscribe to it if you aren't already. There's loads of videos that I think will be helpful for you. Statistics one will be coming soon, and I'll also be doing some more for further maths as well. Okay, good luck with your revision.